Hey, second graders, I hope you had fun studying the rock cycle last week. This week we're going to talk about earthquakes. So what is an earthquake? Earthquakes are the shaking, rolling, or sudden shock of the Earth's surface. They are the Earth's natural way of releasing stress. More than 1 million earthquakes rattle the world each year. The West Coast, where we live, is the most at risk for having an earthquake, but earthquakes also do occur on the East Coast and in the Midwest. Earthquakes can be felt over a large area, but they actually usually last less than a minute. Earthquakes can't be predicted, although scientists are working on doing it. So what actually causes an earthquake? There are about 20 plates along the surface of the Earth that move continuously slowly past each other. When the plates squeeze or stretch, huge rocks form at the edges, and the rocks shift with great force, causing an earthquake. The Earth's crust actually acts the same way as my demonstration here. So I use some Cheez Whiz, and this is supposed to be molten rock. And then I put my graham crackers on top as the plates of the Earth. So the Earth's crust acts this way. As the plates move, they force themselves on each other, gliding. And when the force is large enough, the crust is forced to break. When the break occurs, the stress is released as energy, which moves through the Earth in a form of waves. We feel that, and we call this an earthquake. So again, here we go. We have our molten rock and our plates sitting on top of them. Sometimes the plates might just move apart, and they're moving all the time. Sometimes they might move along each other, and we might feel something slight. But other times they might move with force towards each other, and they're forced to go on top. And this is where we're really going to feel our earthquake. Lastly, I'm going to talk about tsunamis. A tsunami is a large ocean wave, usually caused by an underwater earthquake or a volcanic explosion. Tsunamis are not tidal waves. Tidal waves are caused by forces of the moon, the sun, the planets upon the tides, as well as wind. With a typical wave, the waves flow in circles, but a tsunami, as you see in this picture, the water actually flows straight. This is why a tsunami causes so much damage, because it comes straight at the land. Of course, we can't do anything to stop earthquakes, but we can build buildings and houses to withstand earthquakes. So we're going to do a little bit of the engineering process today. So the engineering process is to ask a question. What's the problem? And then you imagine, try to think of some amazing, awesome solutions. Then you plan, you draw a diagram, or decide what your materials you'll need to solve this problem. And then you build your design. And then lastly, you try to improve on your design. So before we get going on that, we're going to head to the kitchen and make some Jell-O. Hey kids, welcome to Mrs. Kluin's Kitchen. As I told you earlier, our earthquake experiment involves making Jell-O. So I got out my box of Jell-O today. I have a pan, I have a measuring cup, and then I have my glass container for the Jell-O. So I look on the back of the directions of the box for the directions, and the directions for my Jell-O is to take 2 cups of boiling water and add the Jell-O in. After I put the Jell-O into the boiling water, I'm then going to add 2 cups of cold water, and I'm going to put it into my glass container and then put that into the fridge to set. I have a bigger package than you, so you're going to probably use 1 cup of hot water and 1 cup of cold water to make your Jell-O. Also, because of my bigger package, I'm going to have this size glass container where yours might be smaller, because I do want you to have some depth in the container, because you're going to need to stick the toothpicks into the Jell-O. Okay, so I think we're ready to go. With the boiling water, please make sure you have an adult or an older sibling help you with that. And let's make some Jell-O. All right, now that we made our Jell-O, I'm going to show you what we need it for. Go ahead and get out all your supplies. Your supplies are going to be your homemade Jell-O, the marshmallows I provided you, and of course toothpicks. If you're wanting to eat the Jell-O and the marshmallows, make sure you wash your hands thoroughly before you begin, and that way your mom might be more up to letting you eat it afterwards. So here we go. What our plan is today is we are going to design a building. We're going to design our building out of marshmallows and toothpicks. But I want you to put your engineering cap on. I want you to try to think of how you will build this structure so that it actually can withstand an earthquake. So our Jell-O kind of floats and moves kind of like the Earth's crust. So we are going to build a structure and then create an earthquake. So Karina here is going to build my structure. We're going to get to work. You can pause your video now and go ahead and build your own structure. I'll just show you a few things I'm going to do as I move along, but it's going to start like this. And you have to decide, okay, am I going to build a slanted roof? Am I going to build a square? Am I going to build it circular? And you get to design your own building. So put your engineering caps on and get to work. All right, so I hope you guys had fun building your structure. Here's the structure that Karina built. Before we start our earthquake, Karina, why did you build this type of structure?
Because I thought it would stay up during an earthquake because I put it like to the bottom of the Jell-O.
Oh, so she stuck the toothpicks into all the way to the bottom of the Jell-O, and then you kept it pretty low to the ground. Mm-hmm. Awesome. And so here we go. To start, I'm going to take a blunt knife, and I'm going to go around the edges. And then that way, because in an earthquake, remember the plates aren't actually attached. So you want to make sure that they're not attached to the side of your dish. Should we start the earthquake?
Yeah.
Do you want to do it? Okay,
here.
Go ahead and shake. Oh, that's a pretty big earthquake, pretty big earthquake. Let me go a little more earthquake. It's really shaking, it's really shaking. Wow, Karina, it looks like even with all the shaking, your structure withstood an earthquake with maybe a few minor changes that the engineer would have to go to fix your building. So keeping it low to the ground and sticking the toothpicks all the way to the bottom, maybe cementing the structure into the ground really well, seems to have prevented damage during earthquake. Way to go.
Thanks.
All right, so if you did your earthquake simulation and your structure withstood the earthquake, then go ahead and ask yourself another question. Maybe ask yourself, if you added an extra floor to your structure, would it then withstand another earthquake? Those are the types of questions that scientists ask all the time. So once an engineer designs a building, they might say, could I design an even bigger building that would be earthquake proof? And that's how you become an awesome engineer. So go ahead and do some more fun experiments with your Jell-O and your marshmallows, and then we'll be signing off for now, and then next week it'll be volcanoes.